Hi, everybody. Today, oops, don't look. Today, I have some problems for you to do on the first derivative test. I have 6 problems for us today. Shouldn't take us too long. So let's dive in. So I'm going to start us out with a pretty silly example. So the question stated is to identify the function's local extrema in a given domain. And we're going to outline where these extrema are if there are any, and we're also going to make note of which regions are increasing or decreasing. So our first function is f of x equals 5, and it's on the domain from negative infinity to infinity. So what are our steps? Well, we take the derivative, then we find critical points, and then we test regions of increasing and decreasing and make conclusions based off of what we find. So when we have f of x equals 5, we take the derivative. Derivative of a constant is always 0. And we get that this is kind of a silly case. There is no place where before the point the region is negative and after it's positive, or vice versa. So there are no regions of increasing and decreasing since the derivative is always 0. And we'll see that in the picture. Make of it what you will. Trivially, there are no mins maxes, or they're all mins and maxes, however you want to see it. Kind of a cute example just to get us warmed up. So let's do a real example. Now, same question, only this time we have the polynomial x squared minus 4x plus 4. So something that looks kind of parabola-ish. And then we're only going to worry about this function on the interval from 1 to infinity. Here we go. So we take the derivative, we find the critical points, and then we test our regions of increasing and decreasing, and we make conclusions. So here is f of x. We know what it is, x squared minus 4x plus 4, and we take the derivative. So let's do our power rule, and we get 2x minus another power rule problem, minus 4. And then the plus 4 at the very end goes away, derivative of a constant. So we'll set 2x minus 4 equal to 0. Move the 4 over, and we get 2x equals 4, and then divide both sides by 2, and we get x equals 2. So there's our critical point. And quick check, just to make sure it's inside of the domain that we're worried about. It very much is. 1 is greater than 2. Sorry. Ooh, careful there. 2 is greater than 1. So we're safe. Now we plug in 2, and we get that f of 2 is equal to 0. So if it's a min or a max, it's going to be 0. So let's test our regions of increasing and decreasing by taking 2 points, one that's a little bit to the left of 2 and the other that's a little bit to the right of it. And let's see what we get. We get that f prime of 1 is equal to negative 2, and then f prime of 3 is equal to 2. So we get a flip from negative to positive, and we can conclude that 2 is a local minimum, and it's our only minimum. And we're also going to conclude that it's a global minimum since the function is always bigger when 1 is less than or equal to x is less than 2. Think about the fact of what we just calculated right here. Think about how the function's always decreasing when it's less than 2 in this case. So that means everything has to be a little bigger. Think about it. And then we also get that the function increases without bound as we go to positive infinity. So our local min here is actually a global min. And then since the function increases without bound, there is no global max. All right, here's a picture. I didn't cut it off at 1, but you can just kind of ignore from 1 backwards. So we have our global min here at 2, and then we see that it shoots off to infinity, and so there is no global max. All right, moving on. So same question, different polynomial. Make the acronym what you will. Also a different domain. So we're going to worry about this polynomial on the domain from 0 to infinity. And here we go. So here's our steps again. We take the derivative, we find the critical points, and then we test regions of increasing and decreasing, and we make conclusions. So there's our function, and here is its derivative. So what did I do? Started out with that 1/3 x cubed, and I did the power rule. I brought that 3 down. It cancels out with the 1/3, and then you subtract that 3 by 1, and you get x squared overall. Do the power rule to our second term, negative 2x squared. Bring that 2 down, turns into 4. And then you subtract that exponent in the top, and you get negative 4x overall. And then that plus 4x becomes 4. Another power rule. Now, what do? We set it equal to 0, and we notice that x squared minus 4x plus 4 is a nice little perfect square situation. So we get x minus 2 squared equals 0. And we get a critical point at 2. So now we test the regions where a number is a little less than 2, a little greater than 2. Tips and tricks from you boy. Anytime you can fit 1 in a region testing situation, put 1 in there. And if you can fit 0, even better, which now that I'm looking at it, I'm not even following my own advice. But anyway, use 1 and 0 as much as you can. It's very, very nice. So we get that f prime of 1 is equal to 1, and then we get f prime of 3 is equal to 3. Interesting. So there is no flipping, even though we have a critical point. So we're going to get that 2 is not a min or a max, and that f of x is going to have its global min at the furthest point to the left on the domain. And why is that? Well, that's because the function is always increasing. So the furthest to the left that we can get, which in our case is 0, is going to be the minimum. And that's going to be at 0, where when you plug it in, it is 0. And here's a picture. So you can see our min right here at the intersection of the y and the x-axis. And you can see that our derivative does indeed go to 0, and it goes flat, right? If you were to draw the tangent line, it would be a constant function right there with no slope. So we also see that as we go off to infinity, this function shoots off to infinity. Very nice. All right, rinse and repeat, y'all. Let's keep going. So we have a new function. We have f of x equals the square root of 25 minus x squared, and it's going to be on the domain from negative 5 to 5. So what are our steps? We take the derivative, we find the critical points, and then we test our regions of increasing and decreasing, and we make conclusions. Sorry for the repetition, but repetition's good. So there's our function, and we'll take the derivative. Now, I did a couple steps in one, so don't panic. First thing I did was I took this square root right here, and I turned it into the rational power 1/2, and I did the power rule and the chain rule. So you do the power rule, and you bring down that 1/2, and that's where this 2 right here comes from. Then you have 25 minus x squared to the negative 1/2. That's why we put square root of 25 minus x squared here on the bottom. Then you multiply by the derivative of the inside function. So you get this 25 goes to 0, and you get this negative x squared goes to 2x, and that's where that 2x here on the top is. And then I do one nice little last cancellation right here. I cancel these 2's out, and you get negative x over square root of 25 minus x squared. So what do? I don't really need to do much. So it should be very clear that when we plug in 0, the function becomes 0. And there's no like divide by 0 issues. So then we get a critical point at 0. Then you're going to wonder right off the bat, well, what about 5 and negative 5? Doesn't that make a divide by 0 issue? Well, these are technically not critical points in our definition because they are boundary points of the interval negative 5 to 5. They are not interior points. They're not part of the parentheses negative 5 to 5 interval. So we can just worry about them later. And that's what I just showed next is basically what I just said out loud. All right, so We have a critical point at 0. Let's test our regions before and after to figure out what's going on. Hopefully, we've already recognized this to be the top half of the circle with radius 5. And so it should be a global max. And it's going to be right there at the top of the circle at 5, right? So plug in -1 and 1. Look at me following my own advice this time. We will get that it's -1 over root 24. Let's see, did I type this in correctly? Yes, I did. Okay, so we get that f prime of -1 is positive, and then we get that f prime of 1 is negative. So we do indeed have a max at f of 0, which is square root of 25, which is 5. Here's our picture. So one last thing to worry about is our mins. So we'll test the endpoints, and when you plug them into the original function, you'll get that they're both 0. And indeed, here are our global minimums at -5 and 5, which are the midpoints of what would be the total circle. Okay, so let's do another problem. Here we have f of x equals x cubed minus 12x minus 5 on the whole interval -infinity to infinity. This problem is actually going to be easier than the second problem we did because we don't really have to worry about any pesky endpoint calculations or definition issues. Really, it's just going to be a little more computationally intense than anything. And that's not a big deal once you're used to it. So here's our steps. Take the derivative, find the critical points, and then test the regions of increasing / decreasing, and we'll make conclusions. So there's our function, and here's our derivative. I did the power rule on x to the third, and I did the power rule again on minus 12x, and then we knock out that -5 due to the derivative of a constant being 0. Constant functions have no slope, so, or 0 slope. So we set 3x squared minus 12 equal to 0. We are going to move that 12 to the right-hand side, and then we'll divide both sides by 3, which turns out to be 4. And then we take the square root, which is plus minus 2. Okay, so we have 2 critical points, which are 2 and -2. How many times can I say 2? We shall see. So here I am doing some region testing. Try not to get your eyes crossed here. Just notice the broad sweeping results that I have. So the derivative evaluated at -3 is positive after plugging in the numbers. The derivative evaluated at -1 is negative, and the derivative evaluated at 3 is positive. So recall that -2 is in the middle here, and we get a swap from positive to negative. So there's going to be a nice little local max here. And then in the middle right here, we have 2. So there's going to be a swap from negative to positive. We get a local min. So I think I just said out loud what this paragraph says right here. So yeah, we get a local max at -2 and a local min at 2. So one more thing to note is that I didn't really care about boundary points. I didn't restrict the domain. So we need to think for just a moment about what our function does as we go up to infinity. So remember that our leading term is a cubic right here. So if we plug in very, very large negative values, it's going to stay negative. So this function shoots off to -infinity as you go to the left. And when you plug in very large positive numbers, it's going to shoot off to positive infinity. So it's unbounded from above and below. So that means we have no global mins or maxes, but we do have local mins and maxes. And we're going to find that here at -2 and 2. So I didn't tell you what these values are, but not really hard to figure out. Just go plug in f of 2 and f of -2. All right, here's a slightly more interesting example. Here is x to the third times x minus 4. Same question, same deal. Here we go. Here's our steps. Take the derivative, find the critical points, and then test regions of increasing slash decreasing, and then we'll make our conclusions. So here's our function. Here's the derivative. So there's a little bit going on here, but what I really did is the product rule. So I started out and I looked at f as x to the third, and I looked at my g as x minus 4. So we're going to start out by doing a little power rule magic here. Bring down that third, that's where that 3 comes from. Then subtract 1 from the power, and we'll get x to the negative 2/3. That's why there's an x to the 2/3 here on the bottom. Then we'll add, and we'll do x to the 1/3 times, this is a typo. Oh, I'm so sorry. That should be 1. We do the derivative of this function right here, and it will be 1. So please forgive my mistake. What we're going to get right off the bat, just from staring at this bad boy and also pretending that this value right here is supposed to be 1, we get that 0 is a critical point, because if we plug it in, we get a divide by 0 issue. Okay, so, okay, lovely. I fixed my typo down here. This is the true derivative right here, what I have in the orange. So here's some simplification I did. I just combined like terms. I combined, not like terms, I combined fractions. So I raised the x to the 1/3 here to a common denominator. I multiplied it by 3x to the 2/3, and that's just going to be 3x. So you combine the 3x and the x here, and you get 4x minus 4. Factor the 4 out, you get 4 times x minus 1, and we get a new critical point, which is going to be 1. And there's really not much more to do here. So what do we have? We have critical points at 0 and 1, and we're going to test our regions. So we test something a little less than 0 and a little bigger than 0. That's also a little less than 1, and we get that f of negative 1 is negative. Just think about the fact that this value down here on the bottom is positive, and this value up here on the top is negative. And then we plug in 1/2. We get a negative value right here, positive value right here, stays negative. And then we plug in the 2, positive on the top, positive on the bottom. We get a positive value. So the critical point that we had here, which was 0, is not a critical point. Or sorry, it's not that it's not a critical point. It's not a min or a max, because there's no switching from negative to positive. However, we have a switch from negative to positive here. And so we're going to have a local min. And I have a picture for you. I think I just explained out loud what this paragraph said again. Let's see. Oh, we also need to make conclusions about what's global. So let's think about our local min here at 1. Was that where we decided where our thing is? Yeah. Let's think about our local min here at 1. And let's look back at our original function. So plug in really big positive values. The x to the 1/3 is going to be positive. This x is going to be positive numbers. Plug in big negative numbers. We get a negative number here times a negative number here. It's still positive. So as we shoot off to the left and right, the function gets really, really big in every direction. So this local minimum is actually a global minimum. And we'll see that right here with this picture. So one thing to take note of is we have a slightly more interesting case going on here when we have a critical point that is also not a global max or min. If you recall, we did the derivative of x to the 1/3 with the limit definition, and we had problems because when we took the limit as x approached 0, it went vertical. And when it goes vertical, it's kind of like the slope shoots off to infinity, right? And we don't really define that. We get a divide by 0 issue. So, and that's what you see exactly here. We get this slope that kind of shoots off to infinity for a point, and that sucks. And so we don't really have our nice min-max behavior that we want, but we do get the min-max behavior right here. at our point 1. And that is all I have for you today. So have a nice day. Hope you enjoyed the video or at least had a nice ride all the way through. Have a nice day.